Okay, I'm going to wait a few minutes for people to come into this room from upstairs. A few people will be, I expect a few people coming down, and then we're going to start. Is anybody, is Elliot coming down? Yeah, okay, let's just wait for him. I see Zoe. I see Zoe upstairs.
Hi, hello.
Hi, Zoe. And Kaplan is there, Francesco, and then Karim Kanaki is there. Okay, Brian, Paul, Gabe is coming. Should be it. Okay, that should be it here, I think. There are some people in the Institute who are on the Zoom. Right, so this is the last talk I plan to give on this in this course, and Itai Kaplan will take over next week. In fact, next week I will probably, we plan to be in South Bend for a few days, so I'll probably be attending it also on Zoom next week. Okay, so I want to just finish off with a few things, the local stability, the local theory, and say a few things, and then maybe if I've got a time, just state about general stable theories. Okay, and I won't, again, I'll give a few sketch things, and the last thing I did was state a 316, which I just talked about in hand waving, and I will try and write down a few words about that. But just remind you that let's just reminder. I think I said this earlier. I forget when I said it. I said it probably in passing. I mean, so reminder. So again, the same context: T complete theory, monster model, etc., and phi xy. We're going to be assuming typically phi xy is stable now and then, but so phi xy is this L formula, and by a phi formula over a set A, we mean a phi formula, i.e. a Boolean combination of instances phi xb of phi xy. Let's call it Cx, which is equivalent to a formula with parameters in A, such that Cx is equivalent to a formula with parameters in A. Okay, it could be any old L formula with parameters in A. Okay, and we allow to talk about this when A is, say, I allow. Are we okay, Mikhail? Sorry, I made a mistake. We mean, sorry. What is the word? Instances? Equivalent to. Logically equivalent to a formula with parameters in A, where A could be a collection of imaginaries. makes sense to talk about a formula with parameters among the imaginaries because you're in EQ. Okay, and we get as a free formula over A, and S phi of A is a usual thing. It's right. It's the collection of phi types over A, which is the collection of ultra filters on the collection of phi formulas over A. Is that okay? S phi A should be all right. Yeah, it's the collection of phi types over A. Are we okay with this? So you have a phi formula over A. There's a Boolean algebra of phi formulas over A, and it's an ultra filter on that Boolean algebra. Okay, so we call that, and this is something. This is sometimes in literature you talk about phi formulas over A. They mean a Boolean combination of things with parameters in A. Phi form, but it's not right. And we need to have this to make theorems work in a local context. Let me restate theorem proposition 316. We restate proposition 316. So let Pxy be stable and be stable, and let M model of T a subset of M, and Px now a complete type over, this is now a complete type over A. Then, so I write just X for the variable, but a complete type over A. Then there is a phi type over M. And by the way, yeah, I just recall, when A upstairs in that upper board is a model, then actually, if you have a phi formula over M, you can, by task du Vort, choose the parameters of the phi formula to be actually in M. Because there's something saying there are, right? Just so that everything trivializes in that case. So such that Px together with Qx is consistent. So you find a complete phi type over M consistent with P, and Q is definable over algebraic closure EQA, right? I.e., the definition of Q, which is, a phi star formula, is a phi star formula over algebraic closure EQA. That means a phi star formula, which is equivalent to another it's a formula Pcy, which is equivalent to a formula with parameters in algebraic closure EQA. And that makes sense. You work simply in TEQ. The variable y is a real variable, if you want, real variable, but the parameters are in good. Now that's it. And equivalently, to be over algebraic closure EQA is equivalent to have only finitely many images under automorphisms which fix A point by point. Right? This basic model theory stuff. So let me give I've given a hand waving proof in a sense of bye-bye, but I'm going to give a less of a hand wave. I'll give less hand waving proof. It'll in the sense that I write down a few things. So sketch proof, sketch proof. Numero uno, we may assume M is A plus saturated and strongly homogeneous, as I defined earlier, just by passing to such a big elementary extension and proving it over that larger model, and that will A fortiori, whatever your word is, give you the same thing over the smaller model, just by restriction. Okay? definability over algebraic closure EQA, it'll just give you automatically. There's nothing to think about. Well, you've got to think about it, but there's nothing to do. Okay, now part two in the proof, well, by 315, because phi x y is stable, the canonical, the Cantor-Bennigsen dimensional rank of the type space S phi m is less than infinity. Okay, the CB rank of that type. Now let X be the set of QX phi types over M such that PX union QX is consistent. Now, this is a subset of S phi m, and S phi m is a topological space where the topology is given by the phi formulas. All right. Nevertheless, you can check that this X is a closed subspace of S phi m. It's closed. So we have CB rank of, so let alpha be, so let alpha, so CB rank of X is less than infinity. So let alpha be the maximum, be the max of the CB rank in X of Q in X, given by 315. And let Q be such, right? And choose such a Q. And choose such a Q. Okay. Then Q has finitely many images under ought of M, which fixes A point by point, because that automorphism group will act on the space X. That acts on partial types over M. It acts on, right? It'll act on the space X because it's fixing A pointwise, so it fixes P pointwise, and we'll preserve everything, right? We'll preserve the things of maximal rank. So Q is in that, Q is in X, right? So as f of Q, as the CBX of f of Q is also alpha for all f in ought M over A, and there are only finitely many. And there are only finitely many. Such points of maximal rank. Okay, but Q, right? If Q, but Q is defined by Q. This is important, but Q is defined by a so let psi be the phi definition, the definition, or the phi definition, if you want, of Q. So this is a phi star formula over M. So because the conjugates of Q under automorphisms of M fixing A pointwise correspond to the conjugates of the definition, Cy follows that the formula Cy has only finitely many images under automorphisms of M fixing A point by point. So general model theory, Cy is over algebraic closure EQA. Orbit, let's call it finite orbit. Finite orbit under ought M A, and by saturation homogeneity of M, so C is over algebraic closure EQ. Yeah, that's just a general. I mean, that a formula is over algebraic closure EQA if and only has finite many. I mean, just simply, you view the formula as an element of EQ. There's a point in MEQ by coding it by its, canonical parameter. So it's point in EQ. So it says that point has only finitely many images and automorphisms fixing A, so it better be an algebraic closure A. But the point in algebraic closure A just means the formula is defined over algebraic closure A in EQ. So all these things, again, this is super basic things I didn't mention at the very beginning of the course, things like this, because I didn't want to, I thought it was, anyway, that's it.
I just lost the train, but why are you only finding
Because there are finitely many, yeah, of maximal rank. Because alpha, right? So the point was, in 315, we said that if you have a topological space of a compact space with everything gets a CB X, where everything gets a CB rank, then there are elements of maximal rank and finitely many such. Okay, it's like the finite, this corresponds in model, omega stability to maximum Morley rank, and finitely many things of Morley rank. Maximum. Okay, end of that. Right now, proposition 317. Somebody asked last time, so in particular, I should say, this tells you. I mean, the reason I started with a complete type, why the that complete type P can be used for later things. I'm not sure I'm going to use it, but maybe E.T.I. Kaplan asked why I just have the complete type P there. Well, I don't know, but you can use that in proofs, that fact in proofs. But well, I'm not going to actually use it. But in particular, it tells you that any complete phi type over A P has an extension to a complete phi type over M, which is definable almost over algebraic closure EQA, because that complete phi type, let's call it P0 over A, has extension to a complete type over AP, and just apply the proposition for P. And automatically that.
I think you can, Anand, I think you can use this, the complete type, to show there's only finitely many. Over not necessarily algebraically closed sets. Yeah.
Oh, okay. No, I mean, one thing of using it is when you start playing with indiscernible sequences, and indiscernibility in the sense of the big theory, and you have to think about complete types. Then that's one reason for doing symmetry and various. But I'm not going to go through a proof like this, although I was originally planned to. Next thing, uniqueness. Proposition 317. So again, let me just repeat. That previous proposition gives you existence. You take a phi type, a complete phi type over a set A. This has an extension to a complete phi type over a model, which is definable over algebraic closure EQA. So we think of these things as quotation non-forking extensions, okay? And so that's existence. Uniqueness says, again, suppose phi xy is stable. And P1 x, P2x are now phi types over M, and let A be an algebraic closure in EQ set subset of M. Take an algebraically closed EQ. It makes sense. You work in EQ, you work in MEQ. When I say M, I think about that M equals MEQ. It's the same thing. And suppose P such that P1 and P2 are definable over A. Suppose P1 and P2 have the same restriction to A, then P1 and P2 are the same. You can restate this. And here we need to talk about phi types over A. So you have restate. You have two types, P1 and P2, phi types which are definable over algebraic closure EQA. Then they're equal to each other just if they have the same restrictions to algebraic closure EQA. And this just means P1A just means the complete phi type over A, consisting of formulas in P1, which are over A. Where A is, okay, it makes sense grammatically and everything. That's it. Proof. Actually, by the way, in this statement, A is algebraically closed in EQ.
Wait,
Yeah.
What you just said. I mean, usually restricting to A is taking only formulas defined. I mean,
Oh,
you're taking three formulas over A in a much general context. Right?
yeah, I'm using my definition of phi formula over A. So the restriction to A equals a set of phi formulas over A, which are in P. It's the only natural definition
Okay.
given my previous context. Now, I mean, so I'm taking here, and I need for my proof actually, A to be algebraically closed in EQ. But it's also true without A being algebraically closed in EQ, but my proof doesn't give it. But it's also true. Just if P1 and P2 are definable over A with the same restriction to A, then they're equal. But my proof uses algebraic, use the fact that A is. So maybe the people interested in model theory, or if you're interested in stability theory, could just try and prove that in the in the bathroom break or something, unless they're in the bathroom. So proof. Yeah, what is my proof? What is my proof? Right, let C1 be the phi definition of P1, C2 the phi definition of P2. These are both phi star formulas over A. We have to show we want C1y if and only if we want them to be equivalent, right? Because if they're equivalent, then P1 better equal P2, right? Want them to be equivalent. Now, to be equivalent, i.e., enough to see that what for all Q, Y, which will be phi star types over A, C1 in Q, if and only if C2 in Q. All right, two formulas, it's like the usual thing, two formulas over A in normal model theory without phi, two formulas over A are equivalent if and only if they're in the same complete types over A. The same thing for phi star formulas over A. Okay. So let Q be. So let's choose. So choose Q in S phi star A. I want to show that C1 is in Q. So this is just application of symmetry. It's like a kind of, what's it called? You do a magic card trick. You do boom, 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 and there's a proof of something. You know, it's like a bit like a magic card trick. Choose Q in S phi star A, and let Q star be in S phi star of M, extend Q, and be definable over, well, because A is algebraically closed, algebraically closed in EQ over A. By 316 it exists. By 316 we have extension. Precisely that. Okay. Yeah, so by the way, just sorry, in the previous proof, Ibrahim was asking why finitely many. This is precisely the use of CB rank. Exactly the CB rank business. You know, that's the key point it appears. And then maximality of the things, the finiteness of the same maximal points in maximal CB rank. Okay, Q star. Now let chi x be the phi star definition of Q star. So what is phi? So chi. Sorry. So chi is a what? It's a phi formula over A. Right. So by 311 we have this. So by symmetry. So what do we have? We have three types over M. One is a phi star, complete phi star type Q star. Then there are these two complete phi types P1, P2. If you go back to the symmetry, by symmetry, which is 311, chi x is in pi for each I. Chi x is in pix if and only if Cix. So what's Ci? And C1 was the, let's write a list. Chi x is in P1x if and only if C1y is in Q star, right? Likewise, and chi x is in P2x if and only if psi2y is in Q star, where C1 is the phi definition of P1 and chi is the phi star definition of Q star. All right. But what happens? But P1 and P2, but chi is a phi over A. Right? P1, but chi1 is in P1 if and if chi is in P1, if and if chi is in P2. As P1 over A equals P2. QED. Finito. Okay. That shows that C1 is in Q star, if and if C2 is in Q star, and therefore C1 is in Q, right? I.e. so. See, now what happens now? C1 and C2 are formulas over A. But C1, C2 are over A. So C1 is in Q if and only if C2 is in Q, where Q is a restriction of Q star. And that's what we aim for to prove. Okay. Again, if you look at the proof, I'm using the fact that chi, I'm using the fact that A is algebraically closed to get the chi, which is the phi star definition of Q star is over A. So right, so I'm using algebraically closed, but nevertheless, it's true. I think it's true. It's true at least for, it's true in maybe for phi types too. It's true in without A being algebraically closed, as long as P1 and P2 are definable over A. Okay. There's two more things. There's one more thing, is conjugacy in the finite equivalence relation theorem. So the FERT, finite equivalence relation theorem of Shalar, is a kind of, it's more or less, we've more or less done it, you know, but I want to write down properly. Then I want to give the connection with dividing, and which I just not discovered, I just realized there was a much simpler proof that I had in mind, as long as you're willing to work with more complicated objects. Such as what? Such as what? Objects like what? Complicated objects like what? I don't know. Schemes, not schemes. I don't know. More complicated, perfect ordered spaces. You could apply perfect. Bad joke. Sorry. Stupid. Excuse me. Right. Next one. Proposition 318. What is the right board? Can someone tell me what the right board is to pass to? I get a bit confused about these about issues like boards. Where should I go to? Up there?
I think the one you just revealed.
Pardon? I go back to oh, this one. Yeah, you're right. You're right. Thanks, Ken. I mean, this is the kind of help I really need, you know, things like that. Never mind proving theorems. It's just about which board to use. Right, proposition 318, conjugacy and the FERT. FERT stands for finite equivalence relation theorem. Okay. So assume phi xy is stable. Our M model, same situation, A contained in M. I'm not M as a model, of course. I'm not assuming A is algebraically closed, and Px now is a complete phi type over A. As I said before, it's an ultra filter on the collection of phi formulas over A in the sense that I defined. And let Y be the set of Qx in S phi complete types over M, such that Q extends P, and Q again is definable over algebraic closure EQA. So morally, I don't like to use the word morally too much, but for different reasons. But anyway, in principle, this is like the kind of these are the class of non-forking extensions of P. Okay, so extensions of right. Then number one. No. You might think it has. You might think it has. No, before. No.
No, because A here is not algebraically closed.
It's not algebraically closed. Yeah, it's not algebraically closed. Is there a simpler way of seeing this using what I said before? You take this P. There are finitely many things of. Pardon?
If A was equal to ACL EQA, then this would be single.
Oh, yes, you're right. If A equals algebraic closure EQA, this would be a singleton. All right. Yes, you're right. But you still, okay, so it's almost, it looks almost like it's trivial, but, but I think you still have to do something. Okay.
Okay, but then it can't be true what you said before, that over, unless it's always the same.
Pardon?
It's always, you said the uniqueness theorem was actually true for any.
With definable over A. Then one, Y is finite. Two, assuming M is sufficiently saturated, sufficiently homogeneous, saturated and homogeneous ought M over A acts transitively on Y, and 3 for Q1, Q2 in Y, Q1 equals Q2 if and only if Q1 restricted to algebraic closure E, QA, and this we did already. If and only if for each finite equivalence relation E x1, x2 over A. Now, finite means finitely many classes. Okay, not in descriptive set theory, when they say finite, they mean finite classes. We mean in model theory, we mean finitely many classes. All of whose classes are defined by phi formulas, Q1 and Q2 pick out the same class. Okay. Now, let's just make a little quick remark. Suppose I have a such an equivalence relation E. Find many classes, and so E is defined over A, equivalence relation, finite many classes, each given by a phi formula. You take a complete type over M, a complete phi type over M, it better pick out one of those classes, because that complete phi type will say I'm in one of the classes, each class given by a phi formula, so that's a condition to phi formula, therefore by completeness it's in exactly one of the classes. Okay, so this last thing made sense, and this part is already given by proposition 317. Okay.
And
Yeah.
isn't this almost the same proof that we did before, but now we assume that P is a phi type and not I mean, are you now going to say Y is closed and take maximal rank? I mean, is this the proof?
No. I mean, it's not. I'm trying to think. I mean, it doesn't. It's not enough.
Okay.
No, that proof. I could do that proof, and that proof would just tell you that there is. All it would tell you is that there exists a. So given P a phi type over A.
Oh, you need Y to be non-empty.
No, it's not that. No. All that proof would give you is given a complete phi type. So you're right. I could run the previous proof with P replaced by a phi type rather than a complete type. All it would give you was that there is P as an extension to a complete phi type over M, which is definable almost over A. It doesn't say there are finitely many of these things.
Yeah, it will give you non.
Yes, just non-emptiness of Y. You're right, just non-emptiness of Y, not transitivity. You do something else. Okay.
But you have to show that they're actually right. It will be the same step.
You have to show what? You have to show that all the statement gives you. The statement gives you Y is not empty. Yes, gives you Y not empty. But read more than this. Okay, so let's just see what we can do here. Maybe we let me do quickly. Okay, let's start with this. So this is relatively easy, and it's just in some sense it's close to being a restatement of what we did before, but never mind. So let's first do sketch proof. First do 3. So we have, what did I have? I had 3 conditions. I had a condition A and a condition B and a condition C, right? So A if and only if B for 3, A if and only if B is the previous is 317. What about B if and only if C? Well, yeah, it's enough to know that it's enough to know. So to have the same restriction means for any phi formula over algebraic closure EQA, it's in Q1 if and only if Q2. Here we're talking about finite equivalence relations. So it's enough to know. I'll just state quickly, then we'll have a break. Enough to know that if Cx is a phi formula over algebraic closure EQA, then there is a finite equivalence relation EXY, EX1, X2, finite equivalence relation defined over A, all of whose classes are given by phi formulas such that C is a union of classes. It's equivalent to a union of. Okay, it's enough to know this. And why is this? It's enough to know it because it tells you if you pick out, it just tells you then that if you pick out, if Q and Q1 and Q2 pick out the same classes, they better pick out the same formulas almost over A. Right? And why is that? Because I just wave the hand, because you take the formula C over algebraic closure EQA, it has finitely many conjugates over A, fixing A pointwise. There's finitely many images under automorphisms fixing A pointwise, finitely many. C1, C2, Cn. Look at the Boolean algebra generated by these. You take complements, you take just complements in sections, etc. It's finite. And the atoms there are precisely, the atoms are have to be the classes of some A-definable finite equivalence relation, just by automorphism arguments. So that's an easy thing. You just take C1, C, and take its conjugates, and intersections and complementation, etc., generates a Boolean algebra. The atoms will be the classes of the relevant finite equivalence relation. Okay, and that E will be invariant under automorphism, so it's over A. Right, that's it. And then, so that's part of that. Now we have to prove two. Let's have a little break now. And I'll do quickly 2 and 1. Okay. Yes. A few minutes break. Thank you. Is it off now or not? Sorry? Yeah, just because I want to. Yes. Let me see. Everything except for this. That board is still Can you put it back on? Yeah. Okay, so anybody got anything to say, questions or something in the audience? Okay, I'm going to start again. Can I start again? Right. So maybe let's do, I'll do this quickly. It's just, yeah, let's do two. Two is transitivity of transitivity, right? It's the two. So again, in the context of assuming M is sufficiently saturated, we need a sublemma. Little sublemma, which is left to you. We call it star. For any completion, so the context, we have this type P over S phi A, we have Y, for any completion, P prime X, a complete type over A of Px of the type Px, which is a phi type over A, for any completion, P prime is consistent with every is consistent for all Q in Y. So any completion of P to a complete type of A is consistent with every type in Q. The idea is, if not, I just say probably, if not, you take some completion P prime, then there's a formula, and take some Q, then there's a formula in P prime implying the negation of a formula in Q. And sometimes you can pull this down to a formula in, you can pull, yeah. And you can pull this down to a formula in P because you're close to being a phi formula. Okay, that's, anyway, we use this, and then it's easy. Then it's relatively easy. So assume Q1, Q2 are in Y. Okay. Then, all right, so Q1, Q2, then by the sublemma, there is a, by sublemma, let P prime X, a complete type, a complete type over A, be consistent with both Q1 and Q2, in particular consistent with Q1, restricted to algebraic closure in QA, and Q2, restricted to algebraic closure EQA. So there are A, B in my model M, realizing P prime, same complete type over A, such that A realize Q1 over algebraic closure EQA, and B realizes Q2 over algebraic closure EQA. Then, so let F be an automorphism of M over A, taking A to B, because A we have the same type over A. And then it better take, so F, of course, F is an orthomorphism M over A. It acts on algebraic closure EQA. So orthomorphism M over A will preserve as a setwise algebraic closure EQA. So for what we just said, so F takes Q1, algebraic closure EQA to Q2. So F takes Q1 to F of Q1. F of Q1 equals this. So F of Q1 equals Q2 by the uniqueness, the previous uniqueness, by proposition 3.17. Because F takes the restriction of Q1 to algebraic closure EQA to restriction of Q2 to algebraic closure, but F of Q1 will be a non-forking extension of that Q2 to restriction to algebraic closure, will be a definable almost over. So anyway, you use uniqueness to get to Q1 equals Q2. And that's finished, right? Finished. And then the rest of it is, what's the rest of it? We want, and now y is finite is, yeah, so now the rest of it is part what? Part 1, finiteness. So we still may assume M saturated, sufficiently saturated. So we've got Y here. Now ought M over A acts transitively on Y. Let Q be in Y. Y is not empty. It's not empty. Let CY be the free definition of Q. So for all F in ought M over A, F of C is the phi definition of F of Q. But there are only finitely many F of C's because P is over algebraic closure EQA. But there are only finitely many. F of C, as C is over algebraic closure EQA, so only finitely many. F of Q, because F of Q is determined by its definition. Okay, that's it. QED. QED. This is basically the sort of local theory, yes?
Can I just ask, I mean, one consequence of this is that P has only finite extensions with P types over ACL.
That's, in fact, that's actually the proof.
Yeah, but I was just going to say there's a direct proof of that.
Pardon?
I was wondering if one could see that direct.
This is the proof. This is the proof. The convenient proof that all of these things, all of these extensions are consistent with a given complete type over A. Okay? And then you get the, so it's funny, it's really funny that one ends up, you start just with phi types, it looks like just purely combinatorics, you end up in this point of view working with complete types, and because you need to talk about automorphisms, and that automorphisms involves complete types. But I guess you could do everything without passing to that. Right. Okay, now so this is based on the local theory, but I want to make the connection finally with dividing, because I didn't mention dividing and forking, and let's make the connection with yes.
Maybe I missed it, but I probably missed it. But how did you prove transitivity? The action is transitive.
Yeah, I showed it here. I showed you take
Yes.
Actually, any automorph error A takes Q1 to Q2.
Sorry, I wasn't. Yeah.
Well, you can find one. You can find one taking Q1 to Q2. Okay.
Yes. Sorry. Yes.
Okay. Yeah, it's again the fact that every extension, so P is a phi type over A, every extension of P over algebraic closure EQA, they're all consistent with a given complete phi type. And therefore you get transitivity by the action, by that argument here.
That's right.
And that requires a little proof, okay? It's a sublemma. Now, finally, I want to make the connection with dividing. So finally, the connection so I guess the key thing in the local theory so we have phi A B. So A is like an X. So A is say phi independent, phi stable. It's a phi independent from B over A if the phi type of A bar over B has an extension to some M containing B to a phi type, complete phi type over some M containing B, which is definable over algebraic closure. This is the notion of independence, okay, for phi, just for the phi. And you have all the various properties. I mean, symmetry where it makes sense. For symmetry, you better have on the other side something satisfying phi star, you know, where it makes, this is the note, this will be phi independence. Okay, I'm sorry, it's a very small, I'm sorry, this is just, it's unimportant what I've written here. It's not a big deal, but never mind. Dividing. So recall that is a definition 319. Recall definition 319. Let CX B bar be a partial type. A partial type over B bar, where B bar could be an infinite tuple of parameters, some partial type. And then we say that we say CX B bar divides over some set of parameters A, some small set of parameters A, if there is an A indiscernible sequence B1, B2, B3, etc., where B1 equals B, such that the set of formulas, the union of sigma xbi, I less than omega, is inconsistent. That's dividing for a indiscernible sequence B1, B2, such that you plug in sigma B1, sigma B2, take the collection of all these formulas is inconsistent. This is
over is the literal sense, not in terms of your definition.
pardon?
Here when you say it's over B bar, you mean literally. You don't mean
In fact, it's equivalent. I could do either way. I could go either way, but let's do it explicitly. In fact, to be frank and honest, Ray, I'm putting it in the formula to begin with, right? So it's explicit already. It's there. Yeah, good, right. But you're correct. I mean explicitly, collection of partial type. where I exhibit the parameters. Okay. Thank you. Thank you. Then a little remark is (320) sigma x bar b bar divides over A. This is a notion invented by Shalon. It's amazingly pervasive notion. It's amazing how this goes through model theory. It's complete, even homonymity, which surprised me at the beginning. You know, it deals with it explains issues of infinitesimals in homonymity. Something like that. It's connected with so many. Anyway, divides over A if and only if there is some finite conjunction. Let's write it gamma xb of formulas in sigma, which divides over A. And when I take, now I can restrict B bar to be a finite tuple appearing in gamma, just by compactness. You've got a big thing inconsistent, and you just simply apply compactness to get a single formula or conjunction of formulas. So a single formula is responsible, finite conjunction of formulas in sigma, which divides over A, right? Now, proposition 321, this is the final proposition I think we're going to do. Assume phi xy or phi x bar y bar is stable. I'm being a bit inconsistent with my A bars and my B bars. By the way, is David, where's David? Is David here? Are you there, David? Oh, he was writing some notes, wasn't he? Was he in the office? Are you there, David? Never mind, doesn't matter. Yeah. Pardon? No, just because he was writing notes. For stable, let M be a model of T, Px a phi type over M, and a subset of M, then the following are equivalent. Let's me pass to the other board. Equivalent. One, Px is definable over algebraic closure EQA, and two, Px does not divide over A. Okay, that's it, to not divide over A. Right, now, okay, so there's an easy direction. I mean, there's an easy direction, there's another direction, the other direction. And let me just say to the obvious direction first. So the point is that this is a much weaker condition. 2 is visibly weaker than 1. And so how come they're equivalent? You know, that's the thing. And maybe I'll say a few words before we do the proof. Is that yeah? So you have to do something here. Now, when you develop stability theory, the way I'm doing it via definability of types and things like that. There's an alternative way of doing it, which is you go through simple theories. Simple theories, generalized stable theories. Do the whole theory of
dividing, etc., in simple theories, and you do it. I mean, you know, this is well known to people doing SOP1 and things like this, or these Kim dividing or whatever. You just do it, and you get working with dividing or forking, which I'll mention forking later. But just not even local. Just okay. So I mean, simple. Was it done? How much was done for local things in simple theories? Could someone remind me how much was done for local, formula by formula? Very little. Anyway, well, okay. So if you want the full theory, so you anyway do it in simple theories and then specialize to the stable case, where you have somehow uniqueness, and then you get the results out easily. But starting with definability is the basic thing. You've got to do something here. I thought until this morning you've got to do something, and then you can do. I thought it was complicated. Never mind. Let's proof one implies. So proof one implies two. We may assume M is sufficiently saturated. What I mean is, why? Because you replace P by its extension over the bigger model, etc., right? And you can just everything. If you do it for a bigger model, you do it directly for the smaller model. And this means already A is always means A plus saturated homogeneous, strongly homogeneous. Sufficiently saturated, and as P is definable over algebraic closure EQA, then P is invariant under ought of M over algebraic closure EQA. It's immediate because it's definable over this. Whether or not a formula phi x b bar is in P depends on a certain formula over algebraic closure EQA satisfied by the B. So it's invariant, right? But if B1, B2, B3, etc. in M are form an indiscernible sequence, and A indiscernible sequence, then all BIs have the same type over algebraic closure EQA. That's a basic fact. If you have a indiscernible sequence, then all the things have the same type over algebraic closure EQA. Otherwise, there'd be a finite equivalence relation over A, just distinguishing them, but then it would have infinite many classes. Contradiction already. Okay, so that's a basic argument about indiscernible sequences and algebraic closure EQ. So, QED. So it follows that if you take any formula, is that okay? QED. I mean, it says because it says that so if QED, because if some gamma x b bar is in P, right, and B equals B1, B2 is A indiscernible, then there's an automorphism fixing algebraic closure EQA taking B to each of the BIs. So by invariance, by what we just said, ought M over algebraic closure EQA invariance of P, each gamma x BI is also in P. So the set of gamma x BI I less than omega
is consistent. Because if they're all actually inside, so this is the direction. The point is that such a type P is invariant under automorphism fixing algebraic closure EQA, a fortiori, it doesn't divide.
So it only uses invariance. It
Pardon?
only uses invariance.
Yeah, algebraic closure EQ invariance. Yeah, so in fact what we have here is that P is definable almost over A implies P is invariant under automorphisms fixing algebraic closure EQA implies P does not divide over A, as Yatir was saying. Other direction is from this way of doing it. Every way I've done the other direction until this morning or something was complicated. You have to do a lot of stuff. So 2 implies 1. So in every place I've written this down, personally, it's complicated. I mean, whether in geometric stability theory, whether in the notes from 2018, there was a construction, a little bit complicated construction, which I was going to do if I had time. And I thought, funny, why is it so complicated? Funny, you know, what's going on? Why should it be so complicated? And then, so let me give a quick thing that which goes a little bit outside maybe our frame of reference, because I'm using some notions we didn't talk about, if nobody minds. Let me give another. And also, but I'm going to maybe cheat a bit. I'm going to assume for other direction, 2 implies 1. On the face of it, you cannot assume M being saturated unless you use forking in place of dividing. But I'm going to assume it. So make life easy by assuming, so for simplicity, also assume M sufficiently saturated. Okay, now I'm going to use something which is outside the scope of things, but I'm going to use Laskar strong types, general form. So we'll use Laskar strong types. So by the way, I did mention at some point that doing model theory doing stability over sets rather than models brings in this whole machinery of strong types. Now, a strong type over a set A is just a type over algebraic closure EQA. So a strong type over a set A, a complete strong type is just a complete type over algebraic closure EQA. That's called we call it a Shalar strong type. What's been called a KP strong type over A is a complete type over the set of hyperimaginaries which have small orbits over A. So this goes into the realm of continuous logic a little bit. But these are all belong to compact sort of spaces in some sense. Laskar strong type is complicated. It doesn't belong in a compact space. And in fact, there's been a whole 20, 30 years of trying to understand Laskar strong types and the Laskar group as an object, because it's not a compact object. You know, what exactly is it? And anyway, it'll come in the picture here. And there's a recent paper of Udi called Beyond the Laskar Group, talking about, which seems to solve everything I wanted to know. It seems, but I didn't read it yet. Unfortunately, it's like, okay, tells me like stop working now, right? Because everything you wanted to know is there. But I didn't read it yet. Anyway, let's do it. Laskar strong types. So here's a definition. BC, B bar, C bar, a definition. I've got time to do this, I think. B bar, C bar have the same Laskar strong type, L for Laskar, over A, if, in fact, this was kind of this whole thing appeared in the old paper of Laskar, Dan Laskar from 1982, about what was it called? The category of models of a complete theory. It came back into the picture in something we did with Kim in Simple Theories paper. where it plays a role. And some of the definitions I give come from there. Also appears in Casanovis's book about hyperimaginaries, in great detail, things that probably Ten Ziegler. Anyway, if there exists B equals B1, B2, up to Bn, a sequence of tuples, and that equals C, such that for each I equals 1 up to n minus 1, you look at Bi followed by Bi plus 1 begins an A indiscernible sequence. It means that this and this are the first two terms, so these are all tuples of the same length. This person are the first two terms of an infinite sequence indiscernible over A. This definition of Lasker-Strong type. So it's actually, there's an n involved, and that n involves, there is an n. It means that it's not on the face of a compact object. All right, the n could be bigger and bigger and bigger. So really, having the same Lasker-Strong type is the transitive closure of the relation that two tuples begin an indiscernible sequence over A. It's a transitive closure of that relation. That's kind of neighborhood relation, if you want. Good. In stable theories, having the same Lasker-Strong type is the same as having the same type over algebraic closure EQA. You have to prove it. Right. Now, ought and ought, what we call ought, F, ought of, this is with a saturated model M, ought of ought F, I write F here, M over A, this is for strong automorphisms, is automorphism M over M, which fix all Lasker-Strong types over A. Of tuples of any length, actually equals automorphisms of M, fixing all Lasker-Strong types over A, even Lasker-Strong types of infinite tuples, where B bar is an infinite tuple, omega tuple. That's ought F. And this is a group. It's called the Lasker group. And studying a Lasker group has been, an issue. General Lasker group has been an issue on the pure side of model theory for a long time. So step A. First suppose, so what do we have? I'm doing 2 implies 1. We're doing here, did I erase 2 implies 1? Oh, did I erase it? I'm sorry. What?
Oh, the statement?
Yeah.
Yes.
So 2 implies 1. What's the statement again? So we're doing 2 implies 1. So we're doing 2 implies 1. P does not divide over A implies P is definable over algebraic closure EQA. So step 1, suppose, so I'm assuming P doesn't divide over A, right? I'm assuming this. Suppose B1 and B2 in M have the same begin and infinite indiscernible sequence. So I'm here borrowing ideas from the NIP papers, the NIP papers. for a sequence, then for my formula phi x, then phi x b1 is in P if and only if phi x b2 is in P. Okay, for my formula phi, for my given formula phi xy. Otherwise, phi x b1 and not phi x b2 is in P. So let's suppose the sequence is b1, b2, b3. Let's call it, so the sequence, say b1, b2, b3, b4, etc. So phi x bi and negation phi x bi plus 1 is in P for all I equals 1, 3, 5, 7, where the bi's, am I, yes?
What is the sequence?
B1, B2, B3, B4, B5, B6.
Where did they come from?
Suppose, hypothesis, man. Yes, hypothesis. Suppose they begin in sort of.
No, of course, but you're trying to show that the P is definable, right?
Pardon?
Are you trying to show that P?
No, that's like the proof has a few steps in it. Okay.
So this is any indefinable sequence?
No, I'm starting with a hypothesis. This is step 1.
Yeah, but you didn't write anything down.
Okay. Suppose B1. So suppose B1 and B2 begin in infinite indiscernible sequence.
Okay.
Okay. Right. B1, B2, B3, B4.
Okay. This is just a general statement on indiscernible sequence.
Yeah. Okay.
You're assuming that P doesn't divide over A.
Yeah. I'm assuming this. But so far, I want to get a contradiction. I'm just writing things down, which I'm just writing down sentences, right? So far. At some point I say contradicting such and such. Okay. Yeah, good. Thank you very much. Right. Thank you. As P doesn't, right? As P does not divide over A, we're now working with a sequence. So B1, B2, B3, B4 is also indiscernible. We get that the set of phi x bi and negation phi x bi plus 1 I equals 1, 3, 5, etc. is consistent. Okay.
So being consistent doesn't mean that it's consistent with P. Anand?
No, it doesn't, but it doesn't matter. This is a formula in P. And if P doesn't divide, it's a formula in P. If P doesn't divide, every formula in P doesn't divide. So I get as consistent. And this contradicts the formula being stable. In fact, contradicts phi being NIP. Because the NIP formula, if you take a phi xy, you take an infinite indiscernible sequence, it has an eventual constant value.
Isn't it consistent because they're all in P?
Pardon?
So if I understand correctly, sorry, maybe Yatir is speaking at the same time.
What I've done, I've said, all I've said, no, I'm not saying it's in P. I'm simply saying, no, I'm not saying it's in P. I'm simply saying P doesn't divide. The formula phi x b1 and negation phi x b2 is in P. So this formula doesn't divide, but the sequence b1, b2, b3, b4, etc. is an indiscernible sequence over A. And therefore, when you plug in these i's, not 1 and 2 to be 3, 4, etc., you get consistency, contradiction to stability.
The line above, you wrote something.
What did I say?
If you were to write that line.
Sorry, what line?
You have bx1 and not bx2 in P.
Yeah,
That's it. And then the next line, you put them all in P with the rest.
sorry, yeah,
You didn't mean that.
sorry,
You just erase that line.
sorry, error. Apologies. I'm sorry for confusing people. Yeah, confusing the bourgeoisie. Sorry to confuse everybody. Mistake, error, typo. Anyway, okay, so, and that's contradicting. So a mistake, yeah, contradicting. CXY. You can directly contradict stability from having an indiscernible sequence where the values of phi xb alternate, which they're doing here. That contradicts stability. Okay, so we've shown that for B and C bar beginning indiscernible sequence, and therefore, so hence, good, happy. So for B and C bar with the same Laskar strong type over A, phi x B is in P, if and only if phi x C is in P. Therefore, P is invariant under the strong automorphisms because they preserve the Laskar strong types. So P is invariant, is fixed, is fixed by strong automorphisms Fm over A, because they preserve the Laskar strong types. But therefore, the defining formula of P is fixed. So let C be the defining formula. Definition of P, and C is fixed by ought F M over A. But then it's not exactly a black box. You have to check this implies that C is over algebraic closure EQA, because C is an ordinary imaginary. So maybe there's a few things to is over. Yeah, the only things essentially, the only things fixed, only objects of model theory fixed by these strong morphisms of M over A are things which somehow have small orbit under such automorphisms fixing A. But an imaginary, if it's got small orbit, it better be in the algebraic closure EQA, okay? So this gives, it's funny, it gives a, yes?
Does this say that like in an NIP theory, if you have say a global type that is definable over something and does not divide over A, then it's definable over A scaling equivalence?
Yeah, if an NIP theory, so this actually is borrowed from an early lemma. I thought to myself this morning, why is it so complicated, you know? And then
Is that back in the NIP papers? And then
it's not explicitly there, but it's implicit. Yeah. So,
Anand,
yeah.
I think that the more complicated proof proves something stronger, namely that phi is in P if and only if P union P restricts to A union phi doesn't divide.
Yeah, it's true. That was my original proof. Yeah, that was my original proof. Phi is an A if and only if P. That was my actual, yeah. That was the proof that I'd written down first, or that I had from my notes 2018. That's exactly that statement. But it was a bit complicated. It was just complicated. I was taking a sequence of things and should be discernible, and then get another type, and it just was.
Yeah, it's more complicated. It's more complicated, but I think it's stronger in that sense. It tells you when a formula is it explains the uniqueness somehow, because it tells you phi is in P if and only if it somehow.
Yes. Okay. All right. Good. Okay. Good. But anyway, this is a nice another, and also gives what Gabe said in the NIP. In the NIP thing, if it's if something doesn't divide over A and it's definable, then it's definable over algebraic closure EQA, assuming NIP. Right? Yeah. Okay, that's it. Now, I did want to say a few things about stable theories, but if you take a stable theory, then all formulas are stable, and you have the relation now, A bar is independent from B bar over A, where A, if and only if, if and only if the type A bar over B has an extension to a model which is definable over algebraic closure EQA. That means for all formulas, not just for all formulas it's definable. And then you have the symmetry, etc., etc. And in fact, the main characteristic of stability now is uniqueness. I wanted to say something about it, not just, there's a lot of discussion about independence relations and this being fundamental, but in fact, what is crucial is the forking ideal. And the fact that in the stable theories, this gives a 0-1 valued measure. Anyway, okay, I'm not going to say any more about it now because it's now 5 minutes past, but one can formulate stability in terms of uniqueness of non-forking extensions, which means that, well, okay. So I'm not going to say anything more, right? Another 10 minutes, but I think I'll just stop. So that's it, right? And good, thank you very much. Finish.
Thank you, Anand.
Thank you.
Well, Itai will be here next week, and I'll attend it by Zoom, I think. Thank you for everybody for taking part in it. And, yeah.